Welcome. We want to solve numerically. Let us start with the diffusion equation. We have probably solved it earlier too, but for the sake of continuity and for the sake of comparison with the phase field model, it is better to do it once more. So, we have the equation dou c by dou t is equal to del squared c by del x squared some d tilde, which I am always going to assume to be 1, because this t, x, everything is non-dimensional. Okay. So, I am going to do a finite difference scheme. So, and so what happens? So, we have c t plus delta t minus c of t by delta t is equal to, so diffusivity is 1, and I want to do this. So, this is nothing but c x I minus 1 minus 2 c I plus c I plus 1 by delta x squared. Okay. So, let me keep the d tilde, it is 1, but anyway we will keep it for this purpose. So, I am going to do it explicit. So, I am going to take all this to be time t, and so then I know that c at time t plus delta t is nothing but c at the position. So, this is all I at any ith position is time t plus d delta t by delta x squared multiplying this c I minus 1 t minus 2 c I t plus c I plus 1 t. And like we said earlier, I am going to use periodic boundary condition, because when I have the domain like this, for this point there is no I minus 1th point. So, I am going to use that as the I minus 1 point. For this point there is no I plus 1 point, I am going to use this as the I plus 1 point. So, in some sense it is like this. So, we are going to use the cyclic or periodic boundary condition. Okay. So, I want to write now a script which will do this and solve the diffusion equation, and the initial profile that now I am going to assume is going to be a sinusoidal profile. So, let us take a very small system, so that I can run it in a short amount of time and look at what happens to these solutions. Okay. So, let me take a solution, and this time we are going to write it using scripts. Okay. So, I have to go to the directory in which, okay. So, I am going to make finite difference diffusion dot oct. So, that is the file. Okay. So, I am going to generate a script. So, I am going to take some dt so delta t is 0.001, let us say, and then I have h is equal to 1. So, let me call it as dx. Okay. So, it is easier for us to follow, dx is 1, and I am going to call beta as this d times, and let me define d as 1. So, d delta t by delta x squared is beta. Okay. So, that is d into dt by dx into dx. Okay. So, that is my beta. Okay. So, I am going to take a system with 32 points, okay, and the total number of time steps that I am going to run the simulation is 40,000. Okay. So, I am going to remove any old figure. So, that is clear figure. I am going to use hold on, so that I can plot the initial profile as well as the later profile. So, I am going to take m is equal to 1. So, m basically tells how many wavelengths we are going to incorporate in the given domain. So, this is initial profile that I am trying to make. So, for I is equal to 1 to n, okay, what do I do? Old c of I is nothing but 0.5 into 1 plus sine. Okay. What is the sine wave that I take? 2 into pi into m into I into dx divided by n. Okay. So, that is nu c of I. Let me start with 0, end for. Okay. So, I have initialized the nu c to be 0 and old c is a sinusoidal profile, and how many wavelengths are there is decided by this m. So, one wavelength is what we are starting the simulation with. So, let me plot the initial profile. Okay. So, this is for plotting the initial profile. Then I say for j is equal to 1 to n, this is the time loop, and what we are going to do for I equal to 1 to n for every point, what are we going to do? The west point is equal to I minus 1, east point is equal to I plus 1, right. Now, we have to implement periodic condition. So, boundary condition. So, if W is 0, that means we are at the first point. So, for that the west point is the last point, and if east point is equal to n plus 1, that means you are at the last point, then the east point is equal to east minus n, right. So, that is because the first point is the east point for the last point. Now, so nu c of I is nothing but old c of I plus beta multiplied by old c of W plus old c of east minus 2 times old c at the ith point itself, right. So, this is what we have, and we end the loop for the all the points, and so now we update the profile. So, we say for I equal to 1 to n, nu c of I is basically old c of I end for, right, and then I am going to end the time loop. So, this end for is basically for this loop that I am running, the time steps that I am running. So, that is the end for. So, now I can plot the final profile. So, I am going to plot the old c that I have now, and I am going to plot it with the red line. So, red is basically the final profile. So, that we know. So, this is a script. So, I am going to go to Octave, and I am going to source fd diffusion.oct. Okay. So, this is now taking a sinusoidal profile, and it is going to give me what happens at the end. So, we have taken one sinusoidal profile, and the red line is going to say what happens after some time to this profile. So, that is what we are looking for in this case. Okay. So, it is going to take some time, even though it is a very small system, it is not big, it is only 32 points, but it can take long time, especially because we are taking 40,000 time steps. So, I think I forgot to put hold on. So, let me, because I am just finding the final solution, but that does not make sense unless we know what the initial profile looks like. There is a hold on, why did not it? So, let me so I am going to put the hold on here. So, let me rerun again. So, I am going to plot volt C here with a blue line. By default, that is what it should plot. Octave source FD diffusion dot OCT. Okay, it is not clear what is going wrong. So, let me go to a file that I generated. Okay. So, yes. So, here we have the initial profile which is plotted in blue, and the red profile is basically the profile after 40,000 times steps, because each time step is 0.001, it is 40,000 into 0.001. So, that is near about 40 time units in non-dimensional time units. So, as you can see, because this is a purely diffusion equation, whatever be the wavelength, it is trying to go to the homogenized solution. So, it will reach 0.5 everywhere. So, that is the solution that it is trying to get to. Now, we can take the same kind of finite difference code, but with Corn-Hilliard now. So, how do we do that? So, let us write down the Corn-Hilliard equation. So, Corn-Hilliard equation is dou C by dou T is equal to sum m by nv into. So, I am going to go back to the form in which we wrote first. So, dou f0 by dou C minus 2 kappa del power 4 C by del x power 4. Okay. Now, this quantity dou f0 by dou C I am going to call as some g of C, and g of C is nothing but 2 a C into 1 minus C into 1 minus 2 C, right. So, now we want to do, so we are going to use a similar technique like we used last time for the finite difference scheme. So, it is C I T plus delta T minus C I T divided by delta T equal to. So, this is some non-dimensional 1 that I am going to assume. So, this g of C, now I have to take g of C, okay, and this g of C will be taken at time t for every position I, okay, necessarily, minus 2 kappa. Now, this is the fourth derivative for which I have to take the finite difference scheme. There is a del squared. So, there is a del squared acting on this. So, okay. So, the del squared. So, this then becomes, so we have to take the second derivative for g, because del squared dou f 0 by dou c is what we wrote as del squared c by del x squared, but now that is by del x squared acting on c, del squared by del x squared acting on g of c. So, that is going to be g at a position at time t at position I plus 1 minus g I t plus this is 2 times g I t to g I minus 1 t by delta x squared, right. So, this is the first term, and minus 2 kappa, this is the fourth derivative term. So, for fourth derivative term, then we have to go. So, if you have a point and if you have west point and west of west point, and if you have a east point and east of east point, then in this case it is written as C west west minus 4 C west plus 6 C at the ith position minus 4 C east plus C east east. Okay. So, that is what this is, and this is 8 and minus 8. So, this is the discretization, and in this case it has to be divided by power delta x power 4. Okay. So, now you can write this expression. So, C I t plus delta t will be equal to C I t plus some beta delta t by del x squared. So, let us call this as some d tilde. So, it is d tilde delta t by delta x squared with this quantity g I minus 1 t plus g I plus 1 t minus 2 g I t. So, that is one part minus 2 kappa del t by del x square power 4, right, k delta t del x power 4. So, this is another quantity. So, if you call this as beta 1, so this is some beta 2 multiply by this quantity C west west and minus 4 C west plus 6 C I minus 4 C east plus C east east, right. So, that is the discretization, and this is the finite difference discretization, and this is what we want to implement now on the computer. So, here is the code. So, that we first we define delta t and we define, so let me call this as dx, and beta 1 is basically dt by dx into dx, and beta 2 is dx by dx, because kappa. Okay, so, let me put that also, d is equal to 1.0 and kappa is equal to 1.0. So, this basically d into dt, and so this should be 2 into kappa into dt by dx into dx into dx. Okay. So, to make things simpler, so I again take 32 and 40,000 time steps. So, a clear figure, I hold on, and again I take one wavelength, and so I have the old C. So, I have put a sinusoidal profile, nu C is 0, end for, I plot the initial profile. So, that will be plotted with blue by default, and now I have the for I equal to 1 to n, g of I is 2 volt C I minus 1 minus volt C I minus 1 minus 2 volt C I. So, this is how we calculate g. G was 2, A is 1. So, let me define that also, A is equal to 1. So, this is 2 into A into right 2A into C into 1 minus C into 1 minus 2 C. So, we now start the time stepping. We again go W is I minus 1, W is I minus 2, E is I plus 1, E is I plus 2. So, if W becomes less than 1, then that you make it plus n, and similarly E becomes greater than n, you make it E minus 1, and for W also. So, nu Ci is volt Ci beta 1 into GW minus 2 GI plus GE minus beta 2 times volt CWW minus 4 volt CW, and so on and so forth. Okay. So, this is the, now the profile has to be updated. So, this is the new C we got. So, this becomes a volt C now in the next step, and then we keep going for it. Okay. So, this is the code. Now, if we execute this part, so if we source fd Cornelia dot OCT, what do we get? You will see that in this case we have put a sinusoidal wave, and we know that in the case of Cornelia equation the solution should become, if you have a sinusoidal wave, then that part which is having a curvature like this should become a profile which will go to 1, and the lower portion that should go to 0. So, if you take a profile like this, so if you take a profile like this, and in the case of diffusion equation you expect a profile to become like this. In the case of Cornelia, you expect the profile to become like this, right. The profile has come out. So, you can see that the initial profile that we started with is the sinusoidal profile. In the case of diffusion, it became a curve which was going towards a homogeneous 0.5 line, but in the case of Cornelia, it is becoming a curve like this. What I would expect is that it becomes 1 here, and then it forms an interface and becomes 0 here, and there is another interface because of periodic boundary condition. However, you see that this equilibration has not happened. It has this kind of structure because it is going to take some time before the profile becomes the correct profile. That is the problem with finite difference technique, because we are restricted to taking a delta t of 0.001, okay, and that itself is very small, and so the method is there are accuracy problems. Finite difference technique is not very accurate, the error goes as, especially because we are taking the fourth derivative. So, there are a higher amount of error that you accumulate because of this discretization. On top of it, because it is an explicit technique, the time step that you can take is itself very small, and that does not allow me to actually evolve the system for longer duration and get the proper profile. To avoid this is why we use the Fourier transform technique. Okay. So, in the next part of this lecture, I want to show how the diffusion equation and the Cornelia equation are solved using the Fourier transform technique, and there we will see that we will be able to take much larger time steps. So, we can evolve it fast and we can actually go to the equilibrium profile. So, that is what I would want to do in the next part of this lecture. Thank you.